All right, so here we are. This is the first episode of Applied AI, the podcast where we talk of how folks use AI in practice. I'm Victor Montricala, software engineer from Italy. I work for German scale-up Recare, and today I will host this talk with Alexander, which is one of my colleagues, and he's a ML, so machine learning rockstar in Recare. Welcome, Alec.
Thank you for the nice introduction, Victor. It's so nice to be here. I'm Alexander Ivanovsky, machine learning engineer. I'm based in Germany, working also at Recare together with Victor and a bunch of other people. And I'm so excited for the first episode.
Nice. Well, shall we start from just your book? Because you wrote a book about AI, right? So if you want to just tell us what the book is about before we jump into the next topics.
Yeah, so I can give a quick intro. My book is called Beyond the Hype. And honestly, the reason why I wrote this book was purely because of frustration, not in the literal sense, but nowadays, if you take a look at the media, if you take a look at the overall where the global leaders and where the loudest voices are headed, you would either think that you are going to lose your job because of AI, or that we would solve some unsolvable problems by next week. And in reality, this is, at least I see, and my idea with the book was to communicate that there is a massive gap between sci-fi fantasies and sci-fi representations of AI and its actual implementation in practice, in a real business, in a real product, and delivering real value. And as a practitioner, I am seeing a lot of leaders spending significant resources and efforts into AI initiatives without clear strategy. And my goal with the book was simply to communicate some of the experiences that I've gained, some of my perspective on overall where we are now, how we've ended up here, because AI did not come from the sky and now it solves all of our problems, but indeed it's a discipline that is evolving for decades, which we came to this evolution now with this state-of-the-art models. And I hope that the voice, or at least the thoughts, touch to many leaders who actually are in position to make those decisions and to actually deliver and build better products with it.
Well, I think that it's really interesting because I completely agree with you. Like, there is so much hype. I'm also like one of those folks that are really hyped about AI, but when you use AI in practice, even with like the latest flagship models, even like latest one released by Anthropic, right? You have
the Fable one,
Fable 5, like which is an amazing model, but then still when you use it in practice and when you take into account also the costs and the usages within companies, then you start realizing how far we are from an ideal world. And that's exactly why we start this podcast, right? And the fact that I started doing the podcast with you, it's let's say not random, because I think that there is so much misinformation about and ambiguity about AI and LLM models, and I would love you as a machine learning expert to give an insight to everyone about how LLM actually work under the hood, so people understand what an LLM actually is.
So I think also one of the biggest misconceptions simply comes from the fact that a lot of people do not actually understand how the system works. And of course, you don't need to become an expert, or you don't need to dive deeper into various techniques, into various methodologies that are behind building those systems. But I strongly believe that even if you understand just the basics of it in a more pragmatic way, if you know how the stuff works, I believe you would get a better usage, whatever your use case is, whether you're using AI to write code, whether you're using AI to build your product upon, whether you're just using it in an everyday life. And at least when I have this discussion with various kinds of people, either non-technical people or people just with technical experience, but not machine learning or data science experience. I always give this example that you need to think of it as some sort of a system or some sort of like an example of an autocomplete that you have on your phone, for example, that has existed now for a decade maybe, but it's not doing the magic. It's not doing something that like it won't go and write your message or replace you, but instead it's predicting what you are going to type. And this idea, let's consider the idea of the autocomplete, but built on a massive scale, like the large language models are, because the very early generations, for those here listening, you would remember when Copilot came out, when it was literally an autocomplete, but for developers, because previously you had autocomplete on your phone, it was suggesting the next text, but then this evolved a bit into completing your next line of code. Then there were those simple model generating prose, generating songs, generating some small, very targeted text, or actually continuing text. And then this just evolved on a very massive scale, which brought us to the state of the art that we are currently in, where we have very capable large language models, which are of course not simple autocomplete or are not simply predicting the next word or predicting the next token, but are complex machineries that are able to deduce and are able to fit in your context and produce the result that you steer it to. It could be writing code, it could be generating text, it could be generating video, it could be all kinds of modalities, but essentially the core idea starts from here. Like it starts from the process or the lab behind the model, taking a bunch of data. This is usually called the pre-training process, where it depends on the type of the model, but usually it consists of taking a lot of publicly available data from different modalities, from different domains, from different types of problems. Like it could be massive code repositories, it could be massive corpuses of books, it could be massive amount of articles throughout the internet. And from this, it constructs a statistical model, a machinery that is able to reason and to operate within this context. Of course, if you apply this methodology only on code written in a specific programming language, your model will be bound to this programming language. But if you do this on a very massive scale, like as we are witnesses today, as the labs are doing, you end up with a general model, which is very capable of doing generic tasks. And these are mostly of the state-of-the-art models.
If I understand it correctly, it's mostly about like it's statistics, right? Mainly, it's like a way of like predicting, giving a probability for the next output, right? I give an input in, and then there is a probability, and like a better model is considered when the probability for the expected output increases.
Yes, in some broader context. Now there are different ways that this is done. Like in the maybe couple of years ago, this was the de facto way of defining models. They are probabilistic machines that do conditional probability on the given context, so to predict the next tokens. But now we are entering into models which are enhanced with various kind of sub capabilities or sub tools, which have different expertise and different capabilities, but in a very 50,000 feet perspective, it is essentially this. Depending on your task, depending on your input and on your context, it would produce the next most probable output of it. And like one very general metric to evaluate the quality is indeed how close this is to the desired output. Of course, there are open-ended problems where there is simply no one output. For example, one might ask, how would you evaluate generative AI, where it would generate an image? What is the most probable image? There is no one answer. For example, for some problems, it is maybe obvious, and this is where some advanced techniques exist. And also, it depends on the approach taken, but also there is significant amount of reinforcement learning done, because it's not simply taking the text and just learning the language, because you would end up, if you train all of the English data, you would end up with a model that knows English and nothing more. But for example, like you have different people knowing English. Some can write code, some can write books, some can do whatever they are experts in. But that's why there is this reinforcement learning with human in the loop feedback, where the models are trained on performing on different tasks. So you would have this model who has now learned English, who has now learned a programming language, who has now learned statistical operations or statistical background for finance or for banking industry. And then you apply it on a given task, on a controlled environment. Let's say you task it to do some end-to-end code development, and you evaluate it and you reward it. And this is also put into the training of these models. And then you end up with models which have more expertise and are going a step beyond the pure statistical predictions on what's the next code. Because it's not only to, like, if we take a couple of steps back, previously I use this example quite a lot for Copilot. Previously, it was just writing what you see, but it did not have the complete picture. And this is why those models were purely statistically trained. But now we have models like, I would give examples of Claude, of Gemini, that are able to write a complete app. Because in the training process of these models, the training involved rewarding the models or asking the models to operate in an environment which is a full stack application, maybe, where there are set of operations that need to fulfill, set of requirements that need to do, and those models understand the bigger picture, understand what is the end goal that they need to solve. In this case, write an end-to-end application with zero prompt, with one shot, and or generate a full-length video with one shot. And but the idea is this, that like taking the statistical learning on the fixed data that exists, put this into environment which is reinforced, where the model is rewarded when performs good on a task and punished when it doesn't well. So it learns how to operate in this environment, and with this we end up into some.
How does this reinforcement learning actually works? Like, what does it mean to reward or punish the model while it learns?
Yeah, so if you put it in simple terms, let's say when the model builds this statistical model around all of the possibilities that it can do, it can write some code which, let's say we are training a very simple model who is capable of writing code for some backend logic. And if you only take your corpus to be some GitHub repos of such kind of code, it would write mostly what other people write, or what is the standard for this type of things. And here you could derive some metrics, how close your output is to the expected solution, like how it works, and you would end up here. You would create a designated metric. But now imagine you create the environment. Let's say you create end-to-end test with some approach, like you develop the scenarios where you have, for example, if it takes more than 1 minute for the application to perform something, you learn that this is a negative example, and then let's say the training begins, the model would generate one code, would run this experiment in the environment, and then it would see that the metric failed. It is above than 1 minute, or the UI is not built to a level that it is desired. And this needs to be deterministically done by building the environment. That's why there are different modalities, and for different problems, there exist different types of environments. But simply, it's not that the model would say, this is not good and I would not do it, but it would readjust its understanding of the problem and understanding of the programming language, understanding of the pixel space, if it is a visual model, and would be capable of performing better in those environments. Because let's say it's you are training give another example. You're training a model to generate video, and in your environment you put like ways to. It could be deterministic. It could be with human in the loop giving feedback, so reviewing outputs, to have some special effects, to have, for example, color and so on. So the model would, if it's penalized, meaning all of the steps that it takes, for example, to generate a black and white video, would be considered less relevant when tasked to generate a video, simply because in the environment in which it was trained, this was penalized, because videos should be in color nowadays, or this kind of problems. So it's not some kind of magic, but it's just taking this concept of purely predicting the next token into a more next level.
All right, and just to make sure I get it right, is this about also like benchmarking tools, or not really benchmarking, but as you mentioned, human in the loop, where the human evaluates the output and says this is good or this is not, and then based on that, it automatically adjusts some parameters to try to give the output that is expected?
Yes, in some extent, yes, and that's why this process is very important, and that's why, for example, for such industries there exist specialized models for medical context, for autonomous driving, which those models, for example, if you take state-of-the-art large language model and you ask it to drive a car, probably it would fail. I mean, it would maybe find itself driving on normal conditions, like giving, let's say, you make it output command, so these commands go into some hardware that steers the vehicle. This would maybe work in majority of the cases, but then when it comes a situation which is unpredicted, which does not exist in the normal circumstances, then those models would fail. But then you have autonomous driving models, which are while training, where in this case, the problem is to create the environment. So it's not to create the model, because you have the methodology to train a model. But if you are developing such model, your problem would be to create the environment, but to simulate all of the cases that could happen when driving a car, head-on collisions, wet surfaces, and so on, and to build the environment in such way that you have ways to measure these metrics. For example, you could measure how good, with also physics, it handles on wet road in a simulator. So then when you train your model, it would learn and it would readjust the statistical model towards the view, let's say, or its perception of a field of view when driving a car, or all of the sensors. I mean, it's not that simple. It's not that it would only see. There are a bunch of modalities in this example. And then effectively, you would reassess your learning, or your learner, your model, to perform better in this environment. But then if you take this model and task it to perform in medical context, it could terribly fail, because you haven't produced this kind of environment, or this kind of experiments, or simply given as a completely out of scope example, as a child. If you take a child, for example, if their parents are medical professionals, most likely that these children would develop some better than the average child understanding of the medical world, because simply it lives in this environment. But then it depends on the environment in which it is raised and learned to understand differently different kind of concepts. Because to a large language model trained on general purpose data, some scenario would be, okay, you see a head-on collision, what you do? I don't know, I'm scared, or whatever, which the normal person would do.
And just, I'm not sure if this is strictly related or not, but what's the difference? I've heard like different techniques in training these kind of models, like mixture of experts or dense models. What's the difference in these kind of techniques? Because if I'm not mistaken, like mixture of experts, when a single model per se has separate sets of parameters that can be activated, so they don't work simultaneously, but just depending on the task, on the context, it decides to activate certain parameters. So pretty much it's to say, kind of, okay, I'm trained on, I don't know, doing the dishes, I'm trained on mopping the floor, but I'm not trained on, and I have other trainings, and I activate only those that I need for the specific task. Whereas like dense model should be when a model is trained on like a various tasks, and all the parameters are always activated. Like
yes, so you've put this in a very illustrative example, Victor, and it's like in a traditional setting, a dense model performs like, let's say, a generalist person. Like we all know this person who knows everything. Like you can ask them a very deep like political question, you could ask them very technical question, they are generalists. Like by nature, they are generalists. But then, for example, if with such person you dive into some vertical of this question, then probably they would fail, because they have a very vertical knowledge, but they don't specialize in different things. Because if you ask someone who is very well educated for medical question, probably they would answer you to some extent, but from there onwards, you would need a medical doctor to help you. And these dense models, like in a more concrete example, work in a way that like the model is a statistical machine towards all of its concepts that it's learned, and then when you task it to solve a problem, it activates the full machinery. And this of course is very expensive and could lead to poor generalization to different problems. And that's why there is a shift in the recent period towards mixture of experts models, where instead of taking your model, and let's also go back to the previous example of different environments. Let's say if you've created an environment of a financial setting, if you've created an environment of cybersecurity, of writing code, and all of the other things, and you could, of course, go and train your model on everything. But if you activate the full machinery, it could mix concepts. It could be very hard to infer or very slow. And that's why there exists this concept called mixture of experts, where you have different parts of the statistical model specialized for different types of problems. This is achieved during the training. It's achieved during the whole design of the model, of the architecture. And then when you ask the model to perform a given task, instead of activating the full machinery to solve the problem, it first does a form of a reflection where it asks, okay, which part of my machinery is capable of solving this task, and delegates this task to it. Or in another example, let's say you walk into a company and there is a front desk receptionist who is very aware of the structure of the company and what it solves. And when you ask them a question, instead of they replying to you, they direct you to the designated professional. If you have a problem with sales, they would put you to sales. If you have a problem with billing, they would put you to billing. And it works in this way. So in like if we put the two approaches into consideration or into comparison, in the dense model, we have full activation of everything, which could perform good enough, I would say, for general tasks, but would fail for specialized tasks. This failure could be manifested in slow times or simply quality. And on the other hand side, you have the mixture of experts, which is, again, a big model capable of doing majority of stuff, but instead of using its full statistical model of its own world, regardless of whether it's trained on, it uses different smaller sub models of it to perform this task. And with this combination of and this is why I believe.
Do you think it's best? What's best in your opinion? Like which technique to train the models?
I would say depending on what problem you're trying to solve. If you're trying to be if you're building a very specialized model for a very specific use case, for example, you're building a model on some specific types of programming problems or concepts, then maybe a mixture of experts would be overkill for your problem. Because if you're building a model that understands parallel code, then dense model could solve your problem because you need only one designated model. But from my opinion, in the moment when you need to generalize and when you need to have different, or where you have different types of problems, but you want to retain quality in the vertical of the problem that you are solving, then I would say mixture of experts would be the approach that you choose. And that's why the today leading AI labs are leveraging some form of this concepts. If you, for example, if you take a retrospective couple of years ago, when you ask any chatbot to write you something, it would do well. But when you ask it to write code, it could skip lines, it could do some problems. When you ask it to do Excel to generate you a spreadsheet, it would fail. But nowadays, the state-of-the-art models are implementing this form of combination. So you see in majority of the chatbots or CLIs or whatever agentic platforms you use, you would see that when you ask a question, it would do some sort of reflection, either manifested through thinking or through some internal tool calling that is specialized for this problem. So nowadays, pretty much.
That's a very good point. And it's also crazy to think that like until just recently, let's say a year and a half ago, roughly around that time, like these AI agents weren't that useful in production. Yeah. They were nice just for a demo or something. And now instead, like many companies and many developers, including ourselves, are using daily these agents, and they are extremely powerful. So Well, thank you very much for the explanation. And now I would like to ask you, since we both use AI agents to code, but you also develop AI solutions internally. So you have expertise with like LLMs to write code, but also integrating SDKs and using different, let's say, AI model packages. I would love to hear your thoughts about like the trade-offs that you see, like pros and cons. What you think that is the current state of AI models in a production use case, and how much do you think it can improve in the near future?
So I would say here that majority of we are all witnesses that in a broader sense that the model quality is better, and therefore we're getting better AI-enabled products. And here, from my experience, my usage, and my opinion, I believe that we are headed towards a future or towards environment in which it's not about the models, because the models are there. You have powerful models available to you even in very regulated environments, because now the industry or the labs has aligned with the regulatory, so you have those models delivered to you. But the main both problem, challenge, and solution that I see, if we put it in one framing, is that in order for anyone, depending on, regardless of your task, it could be writing code or using AI to write code or to assist your job. It could be building AI products, or it could be performing day-to-day arbitrary administrative stuff. I believe that simply the effort that you need to put is to understand what machinery are you dealing with. Because, for example, you would see that there are this bunch of parameters that the models have, like a temperature, like an effort, and so on. And if you don't understand them, if you don't understand how your model works, how the model that you are using, it would fail to write you a good code, or it would write you like lines of code that you would blindly accept because it's hard to understand, and then you would have problems. If you're building AI solution, if you don't understand what the model that you are using is providing, your solution would fail to excel in the way that you want it. So here, I think that the biggest challenge that everyone should do, from my opinion, given a user of AI, for, let's say in this context, for writing code, or user of AI for doing or assisting their job, or augmenting their setup, or building AI solutions, the biggest challenge is to understand what you have and to use the best of it. And for this, I would say that majority of course, you could spend hours and resources into understanding the model architecture that you have. Majority of the labs provide model cards, provide results on benchmark, very, very detailed, very quantitative. But I think the key enabler for any kind of task that you're doing is the evaluation and the optimization of it. And for example, if you are using AI in your organization or in your day-to-day life to write code, you need to put sort of rules. You need to define sort of skills in order to get code which is desired, or code that fits your paradigm, that fits your problem, that fits your solution. If you're building AI solution or AI-powered solution, it would you could not rely on the open source or the open benchmarks. You need to build your own benchmark with your own set of problems to evaluate how you perform. And this would not only help you broadcast how good your solution is, but would help you understand what are your failure modes and optimize towards it. So I see this as a very interesting challenge and very like motivating challenge to or way to work. Because, for example, like taking again steps back when we had simpler models or less capable models, again, the level of understanding, those who excelled were the ones who understood it. So I think this should be taken now. And luckily, now we have more and more the the tools and the general awareness, because now it's not only a niche of data scientists and people who kind of know what this thing works, but we have massive repositories of skills, massive repositories of guides, how people use specific mode to perform, or what are the failure mode. So this is something that I take very, very seriously and for granted into my personal understanding, both for using AI to write code, for building AI-enabled products, and overall going forward in this direction.
Well, I mean, regarding also the benchmarking, I completely agree. I think that's kind of we are in a point of time where this is a bit lacking in our, let's say, industry. We have benchmarking for all the LLMs and AI models, and we have also like several nice tools like LangFuse that allow us to kind of build internal benchmarking solution, but it's still quite time consuming, and I've noticed not many companies are doing that, and they rely a lot on like the public benchmarks, but they are not good at reflecting how good the model is at doing the tasks that the company needs, like for the skill set and the tasks that are specific to a company use case. So I think that there is gonna be a big improvement on this side in the near future, especially considering also the rise of open source models, because if I'm not mistaken, like I was reading some articles saying that in average they look like they are 1 year behind, like from flagship models. And one of the main problem right now is that like there are companies that still need to transition and buy new piece of hardware in order to enable developers and users to, let's say, run these AI models locally. But the quality of open source models and the hardware are converging towards a point where I think that we are kind of heading towards a hybrid solution. So we had this huge migration of on-premise hardware, right, that went from on-prem to cloud. So this was one of the biggest topics in the last 20 years. And I think that now with AI, we will kind of see the opposite. So I don't know what's your take on this, but like I really see. You recall I had like this task last week where we had to process documents, and there is like there is a regulation. So sometimes you can't use certain AI models because they are not good enough, but sometimes you can't use them because there are regulation in place. So privacy and so on, and the cost of using like certain AI models through like protocols that respect privacy and everything was like for 3,000 documents was a couple of $1,000, and it could have been even more. Let's say with Fable 5, even around 5,000, and now you can get an NVIDIA GX or let's say a new Mac with 128 gigs of RAM that can run AI models locally, and you can achieve the same task. Maybe I'm not saying for free because you need to buy the piece of hardware, but then you kind of pay back for the hardware in one task or in a few weeks. So yeah, what do you think about this? Like, do you see the future more so like hybrid, like I do, or you see that like flagship models are going to be used no matter what?
Yeah, well, I see both from my viewpoint and also where the vendors are headed, both for software vendors, given the huge open source communities that are gaining, also hardware vendors. Now, pretty much any new device comes with some sort of neural processing unit that is capable of at least running some model, and also easier. Also here, there is the commodity and the capability of running, because now it's easier than ever to run a local model than it was ever before, because previously you need to have at least some expertise to do so, but now this is unlocked. And given the regulation in some industries and simply the fact that you cannot give your data to a cloud, I definitely see a a hybrid future in which, of course, you would have the proprietary labs whose job is to develop they put significant resources into developing state-of-the-art models, into crushing some benchmarks that you could never do or that an open source community could take enormous amount of time to do. But definitely for tasks which are well-defined, well-grounded, and well-bounded, I see a future where we could definitely use local hardware or on-premise hardware capable of running open source model, and then maybe for problems which are very heavy duty or rely on some lab specialty, then we would depend on those. But still, I see, and there is significant evidence that we are headed towards this way, with the new open source models being better than the previous generation. That this gap of being 1 year is tightening, and also again, if we take a look, if we take a step back to our previous discussion, where you have the mixture of experts, this could be, from my opinion, taken on another level, where you have your mixture of your different tool set. So for one, you could default to your on-prem hardware to perform one task. You could still rely on some vendor to provide you model as an API to do the inference on their side. And also, if you take a look at...
Sorry for the ignorance. What does inference mean? Because we hear this term so often, but what does it really mean?
Basically, it's someone doing the job, because we have the statistical machinery, whatever it is, but then you need the hardware to give the output to your input, where you describe your problem and to get your input, to get your output. And this is provided, model providers do this, and they charge you per token, which could, for some problems, explode. And if you own your inference, of course, it still costs, it's not for free. You have huge then responsibility to have your inference, because for some problems, maybe some companies, at least how I see it and what signals I've gotten from the industry, there are models that solve that problem, like even now, open source models, but they don't have the resources to run them. That's why they go on for some unregulated industries where it's okay to publish data to the cloud. But essentially, the concept of inference is giving your data to someone. This someone could be your hardware or your cloud, your data center, or some provider to give you the output to basically, in shorter terms, to do the math for you.
All right. Well, thank you for the explanation. Yeah, so it's going to be really interesting, but it's nice to see how fast these models are moving, and also the hardware. And like, speaking about this, like I tried to run some AI models locally, and I managed to run like Neumotron from NVIDIA and Gemma 4, like with 4 billion parameters. And I mean, it's not bad actually, because they have all this nice capability of doing tool calls, so they can do web searches and so on. But of course, there is still a big gap compared to other models when you use for other tasks, like using Gemma 4 for coding with 4 billion parameters. Like, it didn't really work that well. So I'm really curious to see how long it's gonna take to be able to run really powerful models locally to achieve like the tasks that we usually do.
And I think we have at least the baseline is set, I would say, because now we have expectations and evidence of what we can do. And I think for various tasks, this baseline could be achieved quicker, but for some it could take significant time to do so. But I'm very, very excited for this future to see how far we can go, both with open source models, both with state of the art, because this is a race. If the open source community is pushing towards better models, then this motivates the AI labs to deliver better state of the art, and this is at the end benefiting everyone, which is, I think, one of the most exciting things about this industry. It's a race where instead of having a clear winner, you have more motivated, I would say, losers, or like if one model is now beating other models, then those labs are more motivated, or this open source community is more motivated to beat the next. So at the end, the consumer or the user gains from this race. So it's very, very exciting.
Yeah, absolutely. I mean, I've heard great things because I wasn't able to run it, at least locally. I mean, I tried like, for example, Qwen 3.7 Max and Plus, and there is like the open source Qwen 3.5 or 3.6. And for example, for those models, like they are really great that you can do many coding activities, and imagine like you can run it for free. It's just that you need the piece of hardware, so you need to make that investment first. But I believe that in a year, or hopefully even less, we might end up with a model powerful like Fable 5 in like an open source version of it.
Yes.
And that's amazing. That means that like soon enough we should be able to do many tasks with these free models, and I think that that's going to be a game changer.
And I would say especially for very, very regulated industries, because even though there are still providers which operate in this setting, there is still a clear gap for some places, which this approach clearly unlocks. And it's, I think, then it's finally closing the loop for some industries, which is very important. At the end, the value that is there cannot be achieved because of regulation, but with a local approach, it's enabling. So I'm just curious to see how far we can go in those industries, and it's very exciting times ahead.
Me too. And thank you very much for your time. We will end it up here for this session. And if folks like this kind of format, or if they want a more practical one, we can do it. Like if we receive enough comments asking for like I don't know, tutorial about how to set up a benchmark, local benchmark for testing out like these local AI models, or an explanation about all the parameters to adjust the model behavior. That will be also an interesting part. But in the meantime, thank you very much, and catch you tomorrow.
Thank you very much.